So for this like puzzle, basically you just need to find the length of a rectangle whose height is 1, but when it's divided into a square, this is supposed to be a square, but I'm not a good artist, or good at geometry apparently. And this rectangle together can be part of this rectangle, but this rectangle has the same ratio as this one does. So basically, if you break that down into math terms, or I guess like algebra, you can make this A and A because this is a square, and then this is going to be B, whatever's left of the length of the rectangle. And so it's going to be A plus B over A, so that's the ratio of the length over the height. Compare that to this rectangle whose height is going to be B, but their length is going to be A. So A plus B over A equals A over B. So basically, if A equals 1, what does B equal? I went back to edit and I realized I didn't tell you. The number is phi. That's the golden ratio, is that 1.6 number. Okay, so I'm doing a video on the golden ratio, and basically the golden ratio, it's actually like kind of cool. Not kind of cool, like really cool. It started out as, say you have like a rectangle with a length of, or a height of 1, I guess, and a length of phi, which is the golden ratio. And that's the Greek letter that goes like that. So basically you have this rectangle, 1 by phi. If you took a square, a 1 by 1 square out of this rectangle, the rectangle that would be left of the original rectangle has the same proportions of the original rectangle. So that rectangle would also have the proportions of 1 by phi, but on a smaller scale. And what's really cool about the golden ratio is it's like found in so many different shapes. So like if you took a pentagon and all of the sides are 1, so let me draw this out, that would make more sense. Okay, so pentagon looks like that. If all of these sides are 1, if you connect the two endpoints of these sides, that is phi, even though these sides are 1. So it's connected in like all these different math things, even actually in the Fibonacci sequence, which that's someone else's topic, so I'm like not going to get into that, but basically it's a sequence of numbers. And if you make a ratio of this Fibonacci sequence and whatever like number it is, like if it's the first number or the second number, basically the limit goes towards phi. So it's like really interesting. And there's, I think it's called the Dene equation. I watched a little YouTube video about it because I ended up getting really like wrapped up into the golden ratio. Basically, it's like I think it's called the Dene equation. And it kind of defines, it kind of gives a function to the Fibonacci sequence through the powers of phi. It's really interesting. Anyways, so it's shown in like, what's so cool about it is it's like, I don't know, people say it's like the most like naturally appealing thing to the eye, and that's why we see it in like so many different pieces of like Greek artwork. It's in the Mona Lisa. Golden ratio triangles, those are just called golden rectangles. They're just called golden rectangles because they have that ratio of 1 to phi. And then the golden number, actually, phi is, right, I had to look it up. I couldn't memorize an infinite amount of numbers. But it is 1.61803339, and then an infinite amount of numbers. And actually, something I found out that's really cool, so phi is that number, however 1 over phi is equal to phi minus 1, or almost. I guess since it's infinite, I don't think you can really prove that. However, it's like very close. So that's really interesting. And I think if you work out the whole rectangle problem, that explains why. Anyways, yeah, I just want to explain. So I'm going to give like a little slideshow, I think, of all the different like places it can be seen, because it's like, I looked into it and it's like, it's weird how many like things we don't even think about, like it's there. Sorry, before I start the slideshow, I was looking up more places that can be like seen, and I found this really cool thing. Basically, so like the way a star is built also includes the golden ratio. So say A, so I just labeled it A. I watched a video on it, it did not label it A. But like this little bit right there in between, yeah, like that little bit. If that equals 1, then this little line segment here equals phi. This line segment here equals phi squared. And this line segment here equals phi cubed. It's just like, it's crazy how many different things it's in. Anyways, I'll start the slideshow now. So what's so cool about the golden ratio is it creates this spiral. So like, say you have the original rectangle that can be, so this rectangle can be cut into a square, and then the remaining rectangle is the same ratio. Well, because it's the same ratio, it can also be cut into a square and a remaining rectangle. That rectangle also has the same ratio, so it can be cut into a square and a remaining rectangle. This rectangle can be cut into a square and a remaining rectangle, and it goes on and on forever. And so basically it creates this spiral, and that's like what those flower petals and those flower seeds and the pine cones and stuff follow, is that spiral. List up here that I'm reading off, and I'll put the pictures right here. First off, I already said the Mona Lisa, which it's like her face is the rectangle. It'll show that here. Flower petals, which is like, it's weird that the world also follows, and like nature also follows the golden ratio. Hurricanes, different spirals like in the galaxy, nautilus shells, which I don't know what that is. I think it's an ocean thing, but very interesting. Flower seeds, so not only the like petals, but the seeds. And then also the Pepsi logo, which, I don't know, it's cool how like advertisers can use it to like subconsciously make their logo more appealing. I don't know, it's just like, it's weird how math ties into that. And so basically, the whole point of this is I'm saying the golden ratio is this number 1.618 something 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 that basically is like the most appealing ratio to the eye. And so it's everywhere in marketing, it's everywhere in art and architecture, it's everywhere out in nature. It's really cool. I would recommend looking into it.